In this video, we're going to talk about Chatelier's principle. So, Chatelier's principle says that when a stress or a change is applied to a system that was already at equilibrium, the system will respond in the way that best reduces the stress and allows the system to reestablish equilibrium. So effectively, this is a qualitative way, or at least we're going to use it qualitatively, to predict which direction a reaction has to go to get back to equilibrium. So we're imagining the system is at equilibrium, we mess with it, and after we mess with it, what does the reaction do to get back to equilibrium? And so we're going to look at a couple different things, changes or stresses that we can apply to a system. So we can change the reactant or product concentration. For gas phase reactions, changing the pressure or the volume of the system, and then also how do changes in temperature impact the equilibrium. Okay, so first let's consider changing the concentrations of the reactant or product. Right? So we're either going to add or remove compounds. And so in general, when you add a reactant or a product, that's going to shift the reaction, so it's going to run in the opposite direction of whatever you added, right? So if we add PCl5, right, the reaction was at equilibrium, it was happy. Now we've put in PCl5, and so effectively we have too much PCl5 now. And so to account for that, the reaction is going to run to the right to get rid of that extra PCl5 and reestablish equilibrium. So to get to equilibrium, the reaction proceeds to the right, or to make more products. Right? Conversely, if I add more product, if I add extra PCl3, right, we're assuming the reaction was at equilibrium, we add more product, so the reaction needs to use up that product, and so the reaction in that case is going to run to the left. Right? Now, if we take away PCl5, right, we're assuming the reaction was at equilibrium, so it was happy, then we took away some of the PCl5. So to reestablish equilibrium, the reaction is going to have to run to the left to replace that PCl5 that we took away. And same argument, if we take away some of the product, the reaction needs to replace that product, and so the reaction will run to the right. Alright, so for gas phase reactions, changing the pressure or the volume of the container can impact the equilibrium. And so there are three ways that we can consider changing the pressure. The first thing we do is just add or remove some of the reactants or products. And we really just discussed that. That'll have the same effect as we just talked about. We can add an inert gas, right? Something that doesn't have anything to do with the reaction. That'll increase the total pressure in the reaction vessel, but it won't change the partial pressures of any of the reactants or products, and so that's not going to have any impact. What we haven't talked about yet is what happens if we change the volume. When we do that, that will change the partial pressures of the components, and the system will likely no longer be in equilibrium. And so let's look at that third thing more specifically. Alright, so when we reduce the volume of our system, that's going to increase the partial pressure of all the components. Because remember that volume and pressure are inversely proportional. So the most formal way to do this is to consider the coefficients and think about what's happening to Q and how that's going to compare to the original K. But I think that's the more complicated way to do things. I think an easy way to think about this is when we reduce the volume and thereby increasing the pressure, we've effectively stressed the system by increasing the pressure too much. And so to relieve that stress, the reaction is going to shift to the side that has less moles of gas. So when we reduce the volume, that increases the partial pressures of everything. To sort of relieve that stress, the reaction will go to the side that has less moles. Whereas when we increase volume, that's going to have the effect of decreasing pressure. So we've sort of relieved some of the pressure. So to build that pressure back up, what the reaction is going to do is shift to the side that has more moles of gas. And so let's look at some examples here. So we have the reaction 2 moles of P2 react to form 1 mole of P4. So if we want to know what changing the volume, what effect that's going to have, we need to know how many moles of gas we have on each side. And so we just look at the stoichiometric coefficients. I have 2 moles of gas on the reactant side, 1 mole of gas on the product side. So more moles on the reactants, less moles of gas on the products. So when we increase the volume, that's going to decrease the partial pressures. To make up for that, the reaction is going to shift to the side that has more moles of gas. In this case, it's the reactant side. So increasing the volume of that reaction will shift the reaction to the left. It'll actually make more reactants. When we decrease the volume, the reaction is going to shift to the side that has less moles of gas. Right? When we compress it, we're adding the stress of that increased pressure. To release that pressure, the reaction will shift to the side that has less moles of gas. So when we decrease the volume of this system, that's going to shift the reaction to the right. All right, if we look at our next reaction, so now I have 1 mole of gas phase reactants on the reactant side. I have 1 plus 1, I have 2 moles of gas phase products on the product side. And so when I increase the volume, it'll shift the side that has more moles of gas. So in this case, it'll shift the reaction to run to the right to make more products. Conversely, when I decrease the volume of that reaction, it'll shift to the side that has less moles of gas, and so that's going to go to the left. Now, as we'll see in this third example, I have 2 moles of gas on the reactant side, 2 moles of gas on the product side. And so in this case, changing the volume is not going to impact the equilibrium. And this always turns out when the number of moles of gas is the same on the reactant and product side, changing the volume is going to have no effect on the reaction. That change of volume isn't going to remove the system from equilibrium, and so the reaction is not going to have to respond to that stress. Okay, the final thing we want to consider is changing the temperature. And so the easiest way to consider this stress is by treating heat as either a product or a reactant. And so I'll even explicitly write heat on whichever side is appropriate. And so we know that in endothermic reactions, heat is consumed. And so we can sort of think about heat as being a reactant. And so for an endothermic reaction, we've got reactants and heat making products. And so if I increase the temperature, that's adding heat. That's like adding a reactant, and that's going to shift it to the right. For an exothermic reaction, heat is given off, and so we can write heat as a product. And so now let's say I decreased the heat of the temperature of an exothermic reaction. That's going to be effectively lowering the temperature, is going to be removing heat from the system, and so that will shift the reaction to the right. Now, this is the way to, I think, qualitatively approach changes in temperature. But what I do want to mention is that when we change the temperature, it's actually changing the equilibrium constant. And the changing equilibrium constant is what results in the reactant shifting to adapt to those temperature changes. All right, so let's look at an example. So we have the reaction 2 moles of sulfur dioxide reacts with 1 mole of oxygen to make 2 moles of sulfur trioxide. And we're given the delta H for the reaction. We're told that delta H is negative 198 kilojoules per mole. So the sign on delta H tells me that the reaction is exothermic. That means the reaction is giving off heat, and so I'm going to write heat as a product. All right, and so if we then increase the temperature of this reaction, that's like adding heat. Since heat in this case is a product because it's exothermic, to respond to that, the reaction is going to shift to the left. And then if the temperature is decreased, that's akin to removing heat from the system. And so to replace that, the reaction is going to run to the right.